This is section 6.4, confidence intervals for variance and standard deviation. So we're going to interpret the chi-square distribution and use the chi-square distribution table. Use the chi-square distribution to construct a confidence interval for the variance and standard deviation. The point estimate for sigma squared is going to be s squared, and the point estimate for sigma is going to be s. So in the chi-square distribution, our point estimate is standard deviation or variance. In the previous section, our point estimate was the proportion, and before that it was mean. So there's three different point estimates, so you really need to study and make sure you know which one you need for which problems. And looking at the point estimate and the information given in the problem can kind of hint which one you should be doing as well. So s squared is the most unbiased estimate for sigma squared. So the variance is sigma squared, the sample statistic is s squared, and the standard deviation is sigma with a sample statistic of s. So the chi-squared distribution. You can use the chi-squared distribution to construct a confidence interval for the variance and standard deviation. If the random variable x has a normal distribution, then the distribution of chi-squared, which is this is chi-squared, the little funny looking x thing here squared, equals n minus 1 times s squared divided by sigma squared. This forms a chi-squared distribution for samples of any size n greater than 1. So properties of the chi-squared distribution. All chi-squared values are greater than or equal to 0. The chi-squared distribution is a family of curves, similar to what we covered in the t-distribution. To form a confidence interval for sigma squared, use the chi-squared distribution with degrees of freedom equal to 1 less than the sample size. So that remains the same as the t-distribution. The area under the curve of the chi-squared distribution equals 1, as well as the other distributions we have talked about. And the chi-squared distributions are positively skewed. So a degree of freedom 2, you can see right here, is not very wide but very tall. And as the degrees of freedom grows, the curve gets wider and pulled. All of them are pulled to the right. They're positively skewed. So there are two critical values for each level of confidence. Now, previously everything has been symmetric, but the chi-square is not symmetric, so our two values have to be found separately. We can't simply just find one and add a negative to it to find the other. The value chi-squared r represents the right tail, and chi-squared l represents the left tail. So, as before, c is the part in the middle, and what we are finding is what's left over, and we can still do 1 minus c divided by 2. The area here is still the same. The two tails still have the same area, as seen in blue here. It's just, since it's skewed to the right, it represents two different critical values. So, find the critical values to the right and to the left for a 90% confidence interval when the sample size is 20. So, degrees of freedom, we do 20 minus 1 gives us 19. And we know that C is 90, so alpha is 1 minus 0.9, which gives us 0.10, not 0.01, 0.10. So area to the right of chi-square equals 1 minus C divided by 2, so 0.05. And area to the left is 1 plus C divided by 2, which is 1 plus 0.9 divided by 2, which is 0.95. So for the right critical value, it should be chi-square dot inverse dot right, alpha divided by 2, degrees of freedom. So we have 0.1 divided by 2. Notice up here I made a typo. This should be 0.1, because 1 minus 0.9 is 0.1, not 0.01. So down here I plugged in the correct one, 0.1 divided by 2, and 19 degrees of freedom. And for the lower, the left, we just use chi-square dot inverse. So for the right one, we use chi-square inverse dot RT, and for the left, we use chi-inverse. They're both still alpha divided by 2 degrees of freedom. So it's still 0.1 divided by 2 and the 19 degrees of freedom. All right, what if I randomly select and weigh 30 samples of an allergy medicine? The sample standard deviation is 1.2 milligrams. Assuming the weights are normally distributed, construct 99% confidence intervals for the population variance and standard deviation. So the degrees of freedom is still n minus 1, so 30 minus 1 equals 29. P, I want 99%, so 0.99. Alpha, 0.01. And the critical values can be found with chi-squared inverse dot RT and that gives us 52. And then to the left, chi-squared.inv, and gives us 13.12. So now to find the confidence interval, we have a formula that we need to plug it into to find the error to add and subtract. Oh wait, we're not adding and subtracting. We just plug this formula in. So it's very different than it was in the first three sections. So we have n minus 1 times s squared divided by the right critical value, and then take the square root of that. And then to the other side, n minus 1 r squared and the left critical value. And this gives us 0.89 less than sigma less than 1.78. Now, if I wanted variance, I would just not take the square root here. So the left endpoint is 0.8, and the right endpoint is 3.18 when it comes to variance, because I took out the square root. With 99% confidence, you can say that the population variance is between 0.8 and 3.18 milligrams. So in this section, we interpreted the chi-square distribution and used the chi-square distribution table. We used the chi-square distribution to construct a confidence interval for the variance and standard deviation. So this table is just a little summary of what we've covered. The parameters were sigma and sigma squared. The distribution we're using is chi-squared, and the critical values to the left can be found by CHISQ.INV, and to the right, CHISQ.INV.RT. Both of those are alpha divided by 2 degrees of freedom.